Good morning, everyone. We are from Group 10. Want to present about our title, Water Column.
We generally think of the ocean in two main parts, the stratified water column and the reactive seabed. The water column acts like a three-dimensional chemical reactor where sunlight drives photosynthesis at the surface, while deeper layers handle remineralization and carbon sequestration. Vertical layering also creates zones with distinct chemical characteristics, especially important for nutrient availability and trace metals. Below is the seabed, acts both as a filter and an archive. Microbes there break down particles that sink from above, and through processes like bioturbation and pore water exchange, the sediment and overlying water stay chemically connected. This dynamic interface is one of the most reactive and vital boundaries in Earth systems.
Biogeochemical components in the water column include physical, chemical, and biological features, such as suspended seal, phytoplankton, and zooplankton. These components can affect the cycling of elements and energy within the water column. Such as dissolved substances, including nutrient and dissolved organic matter by tasks such as bacteria, algae, and microorganisms. Boyer et al. 2013. Other than that, phytoplankton, which is an algae that forms the base of the marine food web and crucial for primary production in marine ecosystem, can interact dynamically with water column, which is also play an essential role in performing photosynthesis to convert sunlight and nutrients into organic matter and oxygen. Turner et al. 2006. Water column also contain dissolved organic matter (DOM), which are organic compounds derived from the breakdown of living organisms that can potentially influence carbon cycle. Hansel and Carlson 2015. Kepler et al. 2023 state that dissolved inorganic carbon is a major carbon reservoir in ocean, including dissolved carbon dioxide and bicarbonate. Lastly, the water column also contains gases like oxygen that are crucial elements for respiration and microbial processes. Robinson 2019.
Okay, so today I'll be listing all the biogeochemical component in seabed sediment layer. So for a major element in seabed sediment layer, there will be carbon in form of organic carbon and inorganic carbon such as carbonate. And then the next one is nitrogen in form like ammonium, nitrate, and nitrogen gas. And then for next one is sulfur. Including sulfate and hydrogen sulfate, and then phosphorus mainly as phosphate, and then iron typically as iron 3 Fe3 plus and iron 2 Fe2 plus, part of oxide and sulfide, and then manganese formed in manganese oxide and reduced Mn2 plus. So next one is trace metals such as zinc, copper, lead, and then for minerals like silicates are mostly from weather rock material, carbonate mainly calcium carbonate. And then for the gases and dissolved compounds such as methane, dissolved inorganic carbon (DIC) includes.
So I will explain about the interaction between water column and seabed by explaining the soft tissue pump. First of all, during photosynthesis, phytoplankton create organic matter uses carbon dioxide. Then they got consumed by zooplankton, which incorporating this carbon into the body. So this zooplankton move vertical migration into the deeper water daily, so they can respire CO2 at the deeper part of the sea. And then, when this zooplankton or any organism that have carbon in their body died, they release the particulate organic carbon that sink into the deeper ocean. Then, this particulate organic carbon will be decomposed by the bacteria to release the CO2 via respiration. And finally, some of these organic carbon reach the seafloor where it's gathered and stored long term as organic carbon, effectively sequestering CO2 from the atmosphere.
Let's begin with carbon cycle in the ocean. Phytoplankton at the surface absorb carbon dioxide from the atmosphere through photosynthesis, forming the base of the marine food web. As we can see on the image, as they die or are consumed by zooplankton, carbon moves through the food chain and some of it sinks to the deep ocean in the form of organic matter. As we can see from the image beside me, this process is essential for long-term carbon storage and is often referred to as the biological pump. But this natural system is being disrupted with rising atmospheric carbon dioxide. More of it dissolves in seawater, creating carbonic acid, then this leads to ocean acidification. As carbonic acid dissociates, it forms bicarbonate and hydrogen ion, reducing the ability of carbon ions. These ions are critical for marine organisms like corals and shellfish to build calcium carbonate shells and the skeletons.
Human activities have significantly altered natural biochemical processes, particularly the carbon, nitrogen, and methane cycles. The burning of fossil fuels and deforestation increase carbon dioxide emissions, increasing the greenhouse effect, global warming, and stored organic matter released back into the atmosphere. The main source of methane, namely livestock, rice cultivation, and fossil fuel extraction, have a much higher global warming potential than carbon dioxide, despite their shorter atmospheric lifetime. In agriculture, conversion of forests to farmland, over-fertilization, and excessive use of fertilizer disrupt the nitrogen cycle, reducing soil fertility and leading to nitrate pollution in water bodies. In addition, the combustion process releases nitrogen oxides, contributing to air pollution and harming human health and ecosystem.
The ocean's water and seabed work closely together to keep marine life thriving. The water brings in nutrients that support the growth of tiny plants, while the seabed helps by both storing and releasing important elements through natural chemical and microbial activity. This constant exchange, driven by things like sedimentation, decomposition, and the flow between the seafloor and water, keeps the ocean's nutrient cycle and productivity going. But human activities and climate change are putting this balance at risk. They can throw off nutrient levels and speed up harmful processes like ocean acidification and eutrophication. That's why it is important to understand how this system works so we can predict changes and create sustainable ways to protect our ocean for the future.